The week E material talks about types of systems of equations. We're going to talk a lot about linear dependence, talk about what kinds of solutions we might have given a system of equations. So it's going to be a little bit more theoretical in nature. So let's go ahead and talk through it. So we already know that the solution of a linear system, when we're talking about linear system, we're talking about equations where we don't have anything squared. It's not a polynomial. It's each of my variables are raised to a power of 1. And the solution to that system is a set of numbers that satisfies each equation in the system. So if I have this system here, my solution is going to be a value for x and a value for y that fits both equations. It can't just fit one equation, it has to fit both equations. The numerical solution is independent of the symbols in the x vector. We know it doesn't matter what x and y are called. They can be called x, y, z, x1, x2, x3, z1, z2, z3, etc. And then we have two definitions, or two vocabulary words. So the first one is consistent. A consistent system has one or infinite number of solutions. It has at least one solution. Our options are 1, infinite, or 0. There's no range between 1 and infinite. It's either 1 or infinite. An inconsistent system has no solution. Okay, so that's some vocabulary for you. Consistent has at least one solution. Inconsistent has no solution. And we've already seen these types of plots from one of your homeworks. I can't remember. Homework 10, where you essentially graphed the different systems that you had. So here, if I represent my equations as lines, so let's say this is y1 and y2, if I have one intersection point, that means I have a solution. I have one solution between these two lines. Here I had y1 equals y2. Essentially, they were the same equation. They're parallel. There's an infinite number of solutions because there's an infinite number of intersection points. And then the last one we had, y1 and y2, that looked like this, where we had parallel lines, where there's 0 intersection points, which means there's no solution. Vector-wise, if we think about a system equation as a linear combination, which is x1, these values, plus x2, these values, equals b. Okay, so if I look at it this way, this first one represents one solution. So I have my x1 vector, x2 vector, and here's my b vector. So that's one solution. Over here, I have my x1 equals, essentially x2 equals b. They're all the same line. So that means there's an infinite number of solutions. And here I have x1 and x2 right here, and then here's my b vector, which we can see there's no overlap. There's no way I can multiply x1 and x2 by. I can only go on this line, so I can't ever get to b. So we can phrase this in the way that if vectors of A are non-parallel, so if the vectors here, they're non-parallel, these ones are parallel, and non-collinear. Non-collinear means they're not on the same line, which means same line in terms of vectors. So here we're talking about parallel, here we're talking about collinearity. So notice these vectors are on the same line, these vectors are on the same line, these ones are not. So if my vectors are non-parallel and they're non-collinear, the system is consistent and has one solution. If the vectors of A are parallel, so here they're parallel, and they are collinear, all three of them are collinear with the b vector, so this green one's my b vector, then the system is consistent with an infinite number of solutions. And then lastly, if my vectors are parallel, so over here they're parallel and collinear, these ones are collinear, but not with the b vector, the system is inconsistent with no solution. And what this tells us is what kind of equations we can use to represent a system of equations, or it tells us what kind of solutions we might have if we do have a system of equations. So if you're modeling something with higher level equations, then you can go ahead and determine what kind of solutions you might have, whether or not there is a solution, if there's an infinite number of solutions, if there's only one solution, if there's no solution. So it gets into some higher level thinking. But what all of this tells us is if you think back to linear combinations, so think back when we first started talking about linear combinations, we mentioned that a linear combination is C1 V1 plus C2 V2 plus C3 V3 dot 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 equals some other vector, VK, whatever we wanted to call it. That's a linear combination. A linear combination is a system of equations. A system of equations has one solution, or an infinite number of solutions, or no solution. Essentially, what a linear combination tells us, or what a system tells us, is that we need what's called linearly independent equations in order to get a solution. So if we think about this one, those equations are the same. If we think about this one, these equations are the same, they're just offset from each other. These equations are not the same. If we think about it in terms of vectors, these are clearly three different vectors. Here it's the same vector, just different scale. Here I have the same vector, and this one's completely separate. So this leads us to the idea of linear dependence. Linear dependence. Essentially, we're asking, are my equations different from each other? If they're all different from each other, I have this scenario here. I have one solution. If they're not different from each other, then I have one of these. It just depends on what your B vector looks like. But essentially, I'm asking, are my equations different from each other? Are they linearly dependent? So in the next video, I'm going to talk about linear dependence and the different ways that we can